we had three goals we wanted to accomplish. That was to take a patient who initially had a very high level of the virus in his body and either be able to reduce or maintain that virus level, and to give him an additional 10 years of life expectancy without developing AIDS, and then do those two things while minimizing the needed antiviral. So in order to do that, we decided that we were going to take a first principles approach, and so we used a model and then that accounted for the HIV infection in a person. We modified the model to account for the antiviral treatment that we were going to administer, and then taking those equations, we linearized them. We realized it was going to be very difficult to develop the transfer functions by hand, and so then we took our model and put it into the state space form and did our further analysis in using MATLAB and Simulink on the state space model. And we did some stability, found that our gains were stable between about 0 and 10, and then we'd have some oscillations, but we could go up to about 400 with our gain. So with that, we'll jump into Brian's portion. Click again.
Okay. This is the Simulink representation of our state space model. Right here's the transfer function that we were able to obtain. It takes in antivirus count and puts out the virus that'll be in the body. Just a quick explanation on these graphs. As we said before, the person already has an infection with HIV, and we're starting from a value of 744 viruses in the body. And as time starts, that's where the virus count is. And then we try to reduce that to a stable level and keep under that value. We found that the best gain for our controller was a value of -15 through tuning. And so that's the gain that we used throughout the experiment. But we tried different methods to control the virus. Instead of just trying to keep it at just below that level, we thought of different methods that might try to keep our antivirus in total less. Now, over the 10-year life cycle, every patient had a steady state value of 2,600 antivirals delivered. And so our goal was to try to make sure that above that value level was kept to a bare minimum. The model, the graph shown below, is the best model or treatment method that we came up with. We start out by aggressively lowering the antivirus below the 744 line. And then at about 6.5 years, we stop giving any extra antiviral and just stay with the steady state value. And they slowly rise at the end of the 10 years back to that 744 value. And so this was able to minimize the amount of drug delivered. We only delivered around 4,000 to 5,000 units more than our steady state value. Of course, at the end of 10 years, the patient's still at a critical level.
And so just by comparison, these are some other methods of lowering virus count that we attempted. The previous controller was a P-only controller, so then we incorporated the integral action. And we did a similar thing here, found it still worked best this way to apply a lot of more drug early on and then return the AV back to steady state values at about 5 years. This is with a tau of 10. You can see that it uses well over the steady state values and well over our P-only control. And this is the best integral action we could come up with. So for that reason, we decided to stick with a P-only control. Then we tried, we called it a near-death control. And so we set the virus set point at just 10 below the critical level, just to see how much drug that would take. And so you can see at the end of the 10 years, the patient is below the threshold, but total AV is 46,000, well above the 30,000 of the P-only control that we used. So we decided that the best option is to treat the patient aggressively for 6.5 years and then dial back the treatment and let the virus build back up to steady state values at the end of the 10 years.
And then just in conclusion, this table shows those different values, with the 30,000 being the smallest. The optimization approach that we took was similar to that of a computer. It was optimization by guessing and checking. We just weren't quite as fast as a computer, but we tried several methods and found that that P-only control was most effective for delivering on our 3 goals: minimizing the antivirus, keeping the drug below the 744, or keeping the virus below 744, and then getting that 10-year window.